And we will continue on with Katey Alatalo telling us about colder, farther, and with more dishes, studying molecular gas in dead and dying galaxies.
Okay, is this a PDF? Keynote.
Okay. Thanks, everyone, for having me here to talk about galaxy evolution, which I know all of you are extreme experts in, like me. So because of your expertise, I'm actually going to give you a little bit of a background. So when galaxies transform, we start with late-type galaxies, which are the generic spirals that we see. They tend to be disky, they tend to have spiral structure, they tend to be star-forming, they tend to be blue. And early-type galaxies, which will refer to both elliptical galaxies and lenticular galaxies. The thing about early-type galaxies that separates them from late-type galaxies is actually a lack of spiral structure. In fact, they tend to have smooth light profiles like this. They tend to be quiescent, they tend not to be star-forming. The thing that's important about these is at z of 0, that is in modern times, when a galaxy goes from being a late-type galaxy and transitions into being an early-type galaxy, for the most part, that transition is one way. So it's really important to understand the initial conditions that turn a galaxy such as the Milky Way, which is a late-type, vibrant, star-forming galaxy, into a red and dead quiescent galaxy. And we've done a lot of good work on that. So what I have here is a complete list, mostly because of this category, of ways that galaxies can transition between blue and red. So mergers have been studied quite well. Falling into a cluster is actually an extremely good way to do it because you can strangle and choke off the gas supply. Secular evolution is actually a surprisingly good way to do this as well, which is when a galaxy grows a bulge that is large enough that it is able to stabilize its molecular disk against gravitational collapse. Group interactions as well. When you're in a compact group, you actually transition galaxies very rapidly. And the other category, which I used to call the AGN feedback category, but I think new observations have told us that that's maybe not the right term for it. So again, other means you can't say, well, you missed something. The standard way we think galaxies transform, that is, when a galaxy is now, the initial conditions have been met and the transformation has started taking place, looks something like this. You start down here with an isolated disk, maybe you get in a small group. This particular pathway is for mergers, but a lot of the properties that happen for mergers actually happen for all the rest of the galaxies as well. Coalescence, you have a blowout phase and a quasar phase. You decay into a K plus A galaxy, which is actually a post-starburst galaxy. That is a galaxy that doesn't have any ongoing star formation, but has young-ish, that is intermediate age stars. And finally, you hit the red and dead elliptical. The thing that's important about this is actually that there is a phase right here where you remove the star-forming fuel. Problem is, that doesn't seem to be quite the case, and I will readily admit that I just built up a bit of a straw man in this. So the Atlas 3D galaxies, which Atlas 3D was what I did my thesis on with Heiles, looked at about 260 early-type galaxies. They had to be in the north, they had to be within 42 megaparsecs, they had to be massive, and we morphologically classified 871 possible galaxies inside of these constraints, and we found that 261 of them were early-type galaxies. Here they are in a color magnitude diagram, and I'll point out that the Atlas 3D early-type galaxies, which have these shapes right here, sit pretty much in red colors. I'll point out this is a slow rotator, it's an elliptical galaxy, a dispersion-dominated galaxy. This is a fast rotator. They tend to be lenticular galaxies. They tend to be rotation dominated. But the thing that you should notice is that 20% of these red and dead, quenched, morphologically dead galaxies, in fact, have non-negligible reservoirs of molecular gas. So this was the first time a systematic study of these have been done. So this is the first time we can say this complete removal of molecular gas is maybe not necessarily a prerequisite to galaxies quenching. Now, the caveat to this is that a lot of these galaxies have very small molecular gas fractions, so you're not forming a ton of stars out of that molecular gas. But again, molecular gas can still be sitting in situ in early type quenched dead galaxies. So what I did when we did this was I wanted to look at what the gas looked like in these galaxies. How was it forming? How was it configured? Were there some things that we could say about these? Was it circumnuclear, et cetera? So when we started, there were only about 20 CO image early type galaxies. This is the set of early type galaxies from Atlas 3D that Lisa Young's work was able to find had molecular gas. The ones shaded in blue had been imaged already in Plateau de Bure or BIMA. This is what Karma did. We increased the total number of imaged molecular gas in early type galaxies by a factor of 2. And we found a lot of different configurations, a lot of different types of molecular gas. Sometimes it was in disks, sometimes it was circumnuclear, sometimes it was massively disrupted. Here we go. And when we looked at that, we actually also found, work by Tim Davis found that for the most part, these galaxies were actually forming stars about a factor of 3 inefficiently. Well, that's interesting, because again, this is a population of about 40 galaxies. A factor of 2 scatter off of the Kennicutt-Schmidt relation is nothing that we write home about. That's when we found NGC 1266. NGC 1266 is a red sequence galaxy. But it's a lot more than that. Though I'm showing you the MegaCam ground-based imaging of NGC 1266, where you can agree it doesn't look very interesting. It's actually fairly quiescent. HST changed that a bit. Turns out NGC 1266 has a massive molecular disk, 10 to the 9 solar masses of molecular gas, and it has a massive molecular outflow. It has about 100 solar masses per year that is taking part in the outflow. And I said that carefully, and I'll tell you why in a bit. It contains half a gigayear-old stellar population, which is a post-starburst, and it's inefficient in forming stars by a factor of 50 to 150. When we looked at it, this is what the molecular gas looked like. This is great. I'm in a galactic audience. So when you look at this CO spectrum, what does it look like galactically? What would you compare this to in sort of star-forming regions in the galaxy? I'm doing audience participation, so someone has to yell it out or I will. Fine, Herbig-Haro objects. This looks like a protostellar outflow. In galaxies, for the most part, you don't see this. Most of the time, you see rotation-dominated, double-horn profiles. Maybe in something that you're seeing a massively disrupted merger remnant, you're going to see a little bit more Gaussian structure. But this gas out here is actually exceeding the escape velocity of the galaxy. That means that about 2 solar masses per year is actually escaping as molecular. Now we had to try to understand why it was that we had this molecular outflow. We had a very compact molecular disk that should be forming stars extremely powerfully, to the point that if the triggering event, which happened half a gigayear ago in this galaxy, was what drove the gas into the middle, why there's still gas in the galaxy? The answer actually came in the form of what the star formation was doing when we looked at it. So again, here's the Kennicutt-Schmidt relation. It's the relationship between the stellar surface density, or the star formation surface density versus the molecular gas surface density. The idea of this is that most galaxies are forming about 2% of their molecular gas into stars over the course of a dynamical time or a free fall time, depending on whether you look at Rob Kennicutt's work or you look at Mark Krumholtz's work. Mostly it comes down to if you're thinking about the configuration of the GMCs. NGC 1266, unlike the early types, which are inefficient by a factor of 2 or 3, NGC 1266 is inefficient by a factor of 50 to 100. So it's really far off of the relationship. The reason we think that this is the case is because of the fact that there is an AGN-driven molecular outflow punching straight through a very dense molecular core that is currently continuously injecting energy into the molecular gas, and that is actually able to efficiently stabilize that molecular gas against collapse, which is why we're seeing such inefficient star formation. The second that this AGN outflow turns off and the turbulence turns off, we would expect that this gas would start to be able to collapse and be efficient, but right now it certainly is not. That is actually how we think we can lengthen the amount of time that the gas has been sitting in the center of the galaxy without prolifically forming stars. So we went a little bit further with this, and this is now a little bit beyond the work I was doing with Carl, and we looked at Higgs and compact groups, yet another group of galaxies we know to be transitioning. And what we found is, again, we were seeing galaxies that were inefficiently forming stars. In this case, not by a factor of 50 to 100, but by a factor of 30 to 50. Still pretty impressive. The reason, again, seems to be, in these compact groups, we are seeing galaxies that are constantly being gravitationally harassed and torqued by their neighbors. And so we think that that is why these guys are inefficient. Skipping this. So what that means is that this picture, where transitioning galaxies go through this complete removal of star-forming gas, seems to actually be a little bit different than that. Not only did we find NGC 1266, not only did we find Higgs and compact groups, but a lot of new studies have shown that star formation suppression seems to be something that transitioning galaxies go through as a phase. That means potentially you can render molecular gases infertile before you actually have to completely remove it from a system for a galaxy to transform. The next thing we want to do is we want to see if you only have star formation suppression in these special circumstances. And so what we did is we looked at the properties of NGC 1266. We saw that it had shocked ionized gas, and it had a post-starburst stellar population. And we turned it into a set of criteria to look and data mine the Sloan Digital Sky Survey to find out if there were more galaxies like this. And what we found is we found 1,067 shocked post-starburst galaxies, or SPOGs, sitting in the SDSS that we are currently looking into to find out if star formation suppression is something you only get in a very special set of circumstances where you can pinpoint a continuous injection of turbulence, or something that is greater. For instance, just recently, work has been shown that post-starburst galaxies, 50% of post-starburst galaxies still have significant reservoirs of molecular gas. These are supposed to be galaxies that have already completely quenched. They've already completely quenched their star formation, and they have expelled their molecular gas. Obviously, the observations show that that's not the case. And so, the moral of the story. Just because a galaxy appears to have traversed the most active part of its life does not mean that it's past its peak. Many times, these galaxies still have fertile star formation if you only know where to look. And I want to thank Carl.
All right. Thank you, Katie. Questions for Katie? Yes, follow.
What about run pressure stripping? Is where that fit in the picture?
Pressure.
Run pressure stripping from the intergalactic medium.
Good call. Run pressure stripping, so in the little side of the fact that we are seeing a lot of these galaxies, one of them that I didn't mention was Virgo Dwarf 2062, which they actually think is showing star formation suppression based on ram pressure stripping. I haven't looked deeply or carefully at any of the Virgo galaxies that are on their first approach to see if the ram pressure stripping is able to do this. My guess is Adam would know better than me, actually, given that they're studying a lot of the Virgo spirals. We don't see a lot of significant star formation suppression in the Virgo early type galaxies that we looked at. In fact, weirdly enough, we see a higher isotope ratio of 13 to 12 CO in those galaxies, which we think is due to ram pressure stripping. And in particular, my pet theory is that that the GMCs are being ram pressure stripped, and you're left with only the densest GMCs, which is why we're seeing that. So, yeah.
Chris.
Yes, Katie, as you know, we also see star formation suppression in the galactic center molecular clouds. And one of the reasons suggested for that is that they have unusually strong magnetic fields. My question is, what are the prospects for measuring the field strengths in the galaxies you're looking at?
I'm not sure, Chris. I'll have to get back to you and think about it. I'd love to do that, though.
Thanks. I was hoping while passing the microphone, everyone would, contribute to the question. You mentioned that gravitational torques of external galaxies can also play a role. So is the thought that, you could have a galaxy that still has a significant reservoir of molecular gas, but the gravitational torques are somehow heating it? And what are the diagnostics of that? And how do you disentangle that from turbulence if you can't directly see, say, an AGN injecting energy?
That's a good question. So first off, the reason that we think that it's gravitational torques, that gravitational torques can play into it, is a slide that I unfortunately skipped because I realized I was running out of time and had to do my Carl punchline. But what you can see is actually there are significant reservoirs of molecular gas in these Higgs and compact groups sort of way down here where it's very clear that they're red. So in those cases, the footprint of the molecular gas that we're looking at, because we're doing this in an integrated way, is much larger than what we think the AGN can directly affect. In NGC 1266, it's a field galaxy. There are no companions nearby, and the molecular gas is all in about a 300 parsec radius around the AGN. The AGN can do whatever amount of work it needs to on that because it can influence all the gas. So the hypothesis for the compact groups was the gravitational torques, partially again because there's a lot larger footprints of molecular gas. Secondly, we know that these galaxies have shocks in them, which I didn't talk about, because of very enhanced rotationally excited H2 from Spitzer. So we think that this is one of these cases where that's what it is. One of the ways we want to do this is we're going to look at the carbon plus emission, et cetera, from Herschel and start to see if we can get into scales. We can do velocity dispersions to see if there are places, for instance, we can see the shocks coming out through the system where we would expect the most suppression to be taking place.
All right, we're going to have to wrap it up there. Let's thank Katey again. Thank you.